the laminar viscous flow and exact solutions of Navier-Stokes equations. So as we know, by laminar flow we mean that a smooth fluid flow situation in which the fluid is moving smoothly and in a streamlined manner, and not that there is no turbulence that is also in existence. So such flows are known as laminar flows. And for this, as we discussed some of the exact solutions of these nonlinear equations under specific conditions. And these cases will be, of course, for incompressible viscous flow in its general form, and in Cartesian coordinates, when we write these equations, they generate different solutions. And if the geometry is cylindrical, we get different mathematical functions of physics and chemistry, they are generated. So all this depends on the geometry in which the fluid is flowing, and fluid's flow is occurring with a specific boundary conditions. We know that if in rectangular coordinates, laminar flow, and in which the continuity equation can be written as du by dx plus dv by dy plus dw by dz, where u, v, w are coordinates of the velocity vector v. So we can write it as the vectors components u, v, w in the xy direction respectively. So similarly, when we write down the Navier-Stokes equation in the x coordinate direction, then it will be, of course, of this nature. And you can see that they are very similar. They are symmetrical in all other coordinates also, in the y coordinates, in the z coordinates. And if the z coordinate, let's say, is taken vertical, and x and y are in the horizontal plane, then there is supposed to be the gravitational forces that are occurring also, but we have included them in the pressure term, and therefore it is not shown here specifically. And of course, the parameters nu is what we call as kinematic viscosity, and if we divide the kinematic viscosity mu by the density of the fluid rho, then this ratio is known as dynamic viscosity. And dynamic viscosity is denoted by nu, whereas mu is coefficient of viscosity. And the del square is the well-known Laplacian operator, and this is in vector notation, and if I have to write it explicitly, it's something like second derivative with respect to x square, second derivative with respect to y square, and second derivative with respect to z. So Laplacian operator in rectangular coordinates is equivalent to that and is known as Laplacian. It can operate on any function, let us say psi or v or whatever, and it will be showing on the left hand and right hand side. Because of the incompressibility, and the Mach number is always taken to be vanishingly small. This is to indicate, this is to make sure that the flow is kept laminar. And we have already defined right in the beginning that the fluid flow that will be considered in these cases will be a laminar flow, so no turbulence there. And you will recall that there will be turbulence if the Reynolds number is very high, and so similarly the Mach number can be estimated to be high. Vorticity and stress related and the stress components are defined and specifically, explicitly written in the form as this. If omega is the vorticity vector, the rotational effect, then its x component, y component and z components are given in equation 5. Similarly, the stress components are given here, and you can see altogether we have these 9 numbers. So 6 of them are taken care of in equation 6, part 2, and the first one that occur in the stress determinant or stress matrix that we write, then these are the diagonal terms, while these are the terms that occur that are written in other places of the stress matrix. So separately writing, the components are written in this form. And of course, we can write all these equations in other coordinates, such as when I talked about cylindrical coordinates, we write it in r, theta, z, that is that is how we take. And if it is spherical, then we take them in r, theta and phi coordinates. So the nature of the equation change, and resultantly, and as expected, the nature of the solutions, that also changes.